Hello and welcome to our poster. I will present the paper A Generic Unfolding Algorithm for Manifolds Estimated by Local Linear Approximations. So the outline of this presentation is we begin with asking what is actually manifold learning. Then we go through the contributions of this paper, followed by some results and a quick discussion and conclusion. So what is actually manifold learning as we know it in machine learning? Is it learning in embedding? Is it learning to visualize your data? Is it unwrapping or unfolding a manifold or your data? Is it fitting a structure to a data point cloud? Or is it all of the above? This is what we see in most new machine learning papers, a mix of all of these things, right? So we have some minimal requirements when it comes to manifold learning. We have a dimensionality reduction step, and then we have an unfolding, unwrapping, or some other strategy in the final step that tries to remove nonlinear and sometimes unwanted structure in our data. So the goal in this work was, what if we try to isolate the actual unfolding part of manifold learning, creating an algorithm that exclusively focuses on actually unfolding a manifold. Right? So how do we go about to do this? We begin with some quick assumptions. First, we need an isometric manifold. This is overlooked in a lot of papers, right? Only manifolds that are isometric to the Euclidean space, in other words, flat manifolds or zero curvature manifolds, these are the only ones that can be properly unfolded. Secondly, we assume our manifold is embedded in Euclidean space of higher dimension than the manifold itself. Thirdly, we assume we have access to local linear approximations of the manifold. Basically, a collection of tangent spaces on the manifold. So, our algorithm is based on two simple constructs from geometry. First, a geodesic along a manifold always has zero curvature, which means it can always be unfolded. This is by construction. Second, a collection of tangent vectors at the point on your manifold can be transported along these geodesics using parallel transport. So with these two things, we create a really simple algorithm. So we now assume we have a collection of local linear approximations at some points on your manifold. We call this charts for now. So how do we do it? We begin with selecting a reference point to where we want to unfold our manifold. Then we calculate the geodesics from the reference point to the origin of all of our local linear approximations, basically the points on the manifold where the local tangent spaces are estimated. Then we transport all local linear approximations, basically charts, along the geodesics towards the reference point. So now we have collected all our local linear approximations at the reference point. Then we unfold all the geodesics directly by setting to zero the last capital D minus D coordinates of the tangent vectors of the geodesic. Capital D is the dimension of the Euclidean space, the ambient space, and the lowercase d is the intrinsic dimension of the manifold. So now we have unfolded geodesic, so now we can send our collection of charts back along the geodesics to its origin point on the unfolded geodesic. So this gives us a really simple and direct unfolding of the manifold. We see it here in the Swiss roll dataset. We send the local linear charts to the reference point, all of them. Then we unfold the geodesics here, and then we send the coordinates back out. This is shown complete in the figure below to the right. So we don't have time to show all the results in this talk, but we have some results here. We have what happens if the manifold breaks. If we try to unfold a manifold that is not isometric, it will break, and we have the MNIST ones. Then we have some other results. We encourage you to check out the paper and the slides here. So finally, to conclude, we have a simple framework with clear results. This is not at present quite crude approximation and not directly scalable. That's the downsides of the algorithm. Future work includes a distortion measure to measure the performance, extending this to really high dimensions, and then convergence guarantees for the quantities involved. So that is it. Thank you for checking out our post.